Hello, welcome back to the course Materials in Sports. In this lecture, we will explore wearable technology and its role in sports, whether in monitoring performance and injuries, supporting training, or enhancing recovery. Our focus will not be on consumer devices such as fitness watches or activity bands. While these tools are excellent at tracking movement and measuring physiological parameters such as heart rate, we will instead concentrate on applications of wearable technology in competitive sports. Specifically, we will look at how these technologies are used to monitor biomechanics and kinematics with the goal of identifying areas for performance improvement, enabling early detection of overtraining and injuries, and optimizing recovery strategies. Before we move on to case studies, let's begin by introducing the concept of wearable technology through a simple diagram that illustrates the different levels of electronic integration in wearables. Wearable technology includes a wide range of devices, from accessories such as watches, bands, and rings, to fully electronic clothing. Within electronic clothing, we can distinguish two main approaches: non-embedded systems, where electronic components are housed in pockets or small compartments, or embedded systems, where components are permanently integrated into the fabric or where the fabric itself functions as an electronic material. In sport performance analysis, motion capture is considered as the gold standard to monitor athletes' movement. Optical systems use cameras to track passive or active markers placed on key anatomical landmarks, enabling the capture of full body motion. However, because of their camera setup, optical motion capture systems are limited by their capture volume and are generally restricted to laboratory environments. In addition, the large number of markers often required makes preparation time-consuming and can interfere with the natural execution of movements. Wearable technology offers an alternative approach that has the potential to overcome these limitations. A variety of sensors can be used, including inertial measurement units, IMUs, and microelectromechanical systems, MEMS, which typically combines magnetometers, accelerometers, and gyroscopes. In rugby, football, or soccer, GPS units worn on the upper back allow practitioners to measure variations in workload across player positions and to assess the intensity of match play. Commercial devices are mainly based on multi-GNSS receivers like GPS, but with access to more satellites to improve accuracy, signal reliability, and coverage. For example, in stadiums or urban areas where tall structures can block satellites. Those devices can track with the accuracy of centimeters the distance covered by the athlete and the speed. Moreover, GNSS receivers are coupled with IMUs for fine details: acceleration, rotation, jumps, impacts. In simple words, the GNSS receiver captures the big picture, while the IMUs get the details. Together, they give coaches and sports scientists a complete movement profile. These tracking systems can connect with additional sensors via Bluetooth, heart rate monitors, possibly EMG garments, for a better understanding of exertion and muscle activation. But hardware alone does not define the value of a performance system. Algorithms and data analytics are what transform raw sensor data into meaningful, actionable metrics. For example, an IMU-based platform targeting jump performance can measure acceleration during a jump, but it is the algorithm that converts this information into jump height, landing force, or fatigue estimations. Many systems today use AI to provide insights on player load, movement efficiency, and injury risk. In today's sports technology landscape, hardware sets the foundation, but algorithms and analytics determine the practical usefulness of the data. Two systems using the same sensors could produce vastly different insights depending on the sophistication of their software. In essence, the combination of accurate sensors with advanced analytics is what gives sports performance systems their true competitive advantage. The rate at which a wearable device collects data is crucial for accurately monitoring, and it varies according to the type of movement and the variables being measured. Guidelines for determining this rate often refer to the Nyquist-Shannon sampling theorem, which specify that the sampling frequency should be at least twice the highest frequency present in the signal to capture all its information. If the sampling frequency is set too low, important data may be lost. Besides kinematics, other useful information for athletes and coaches can also be derived using surface EMG, which stands for electromyography. Electromyography measures the electrical activity produced by skeletal muscles. Electrical potentials generated during muscle contractions are detected with electrodes and analyzed for timing, intensity, and coordination of muscle activation. Electromyography, EMG, helps assess muscle activation and fatigue, enabling optimization of training technique and injury prevention in sports. The use of EMG encompasses several sports. For instance, in running, EMG reveals activation timing of hamstring, gluteus, and calves to optimize stride mechanics. In cycling, EMG can be used to study pedal stroke efficiency and fatigue pattern in quadriceps and hamstrings. In strength training, EMG compares exercises, for example squat versus leg press, in terms of muscle activation to guide exercise selection. Examples of wearable devices for injury detection are also available. For instance, the instrumented mouthguard, a wearable device embedded with sensors such as accelerometers and gyroscopes, designed to capture biomechanical data, particularly head kinematics like acceleration and angular velocity during sports impact. These mouthguards collect data on the frequency and magnitude of head impacts, particularly in contact sports like rugby, to help prevent concussions and manage player health, sending alarms to coaches and medical staff. By identifying players at risk of excessive head impact exposure, coaches can adjust training loads and techniques to minimize injuries. The Men's Six Nations tournament introduced the use of instrumented mouthguard in 2024. Another big field of research is wearable sensors for monitoring biomarkers in biofluids such as sweat. Sweat contains a range of electrolytes, metabolites, and hormones that can reflect hydration, fatigue, and stress. In sports, the most relevant sweat biomarkers today are sodium, chloride, sweat rate, and lactate, since they directly influence hydration, performance, and recovery. Emerging research is pushing cortisol and glucose as next-generation targets. These sensors can be colorimetric. They are based on the change of color of reagent in response to the concentration of a substance in sweat, or electrochemical. They measure an electrical signal related to the concentration of the substance in sweat. One example is GX Sweat, a patch developed by Epicor in collaboration with Gatorade, available in the US market. Before concluding this lecture, it is worth highlighting the materials and technologies that enable wearable devices. Most of these systems are active devices, meaning they require an external energy supply to operate. A typical wearable consists of sensors, which detect physical properties and convert them into measurable signals, a microprocessor that processes raw data, memory to temporarily or permanently store information, a communication module to transfer data to external devices or cloud services, and a power source, usually a rechargeable battery. Naturally, the materials involved are those commonly used in electronics. While miniaturization and flexible electronics are major enablers of wearable technology, they are complemented by a range of other innovations that make these systems practical and efficient. For example, conductive materials that alter their electrical properties in response to environmental changes can serve as sensors. A well-known case is conductive polymers, which respond to mechanical deformation and can be employed in pressure or stretch sensors to monitor body movement, posture, and breathing. In this picture, you can see a textile-based pressure sensor. It consists of an insulating fabric layer placed between two conductive layers. When pressure is applied, the conductive layers make contact through the insulating layer, generating a measurable signal. These sensors can be inserted in shoe soles for gait running analysis. The substrates used in flexible electronics are typically polymer films such as polyester or polyamide, with mylar being a common example, or textiles, which can be either woven or non-woven. On these substrates, various types of conductive inks can be printed, traditionally based on metals such as copper, silver, or to a limited extent gold. More recently, advanced materials like carbon nanotubes and graphene have also been employed to enhance conductivity and performance. The figure illustrates a printed circuit on fabric, where the conductive paths are formed using a graphene silver composite ink designed to achieve high conductivity for wearable electronics applications. Now, let's recap the key concept from this lecture. Wearable technology is still in its early stages, yet its potential applications in sports are already vast. The miniaturization of devices has made them more comfortable and unobtrusive, encouraging athletes to adopt them more readily. At the same time, the development of advanced algorithms capable of extracting meaningful patterns from large datasets offers powerful tools to enhance performance analysis, support coaches in designing effective training strategies, prevent injuries, and detect signs of overtraining at an early stage. Looking ahead, we can expect to see even more innovative solutions emerging in this field. I hope you found this lecture engaging and insightful. This concludes my series of talks. Thank you for your attention.